Okay. Thank you very much for the invitation, and thank you very much here in the morning. It feels really a little bit overwhelming to know that there are so many of us who. It's very nice to know uh, that there are so many of us and to be part of it. Thank you for the invitation to be part of the community, and thank you for being here. Okay, so today I'm going to tell you about my recent joint work with Daoji Huang, Mateusz Michalek, Botong Wang, and Shouda Wang about realizations of homology classes and projection areas. I'll shortly tell you what that is all about. So there are two basic questions. The first one in convex geometry and the second one in algebraic geometry. The first one has a very simple formulation and it has a very nice answer. So it's a good thing that we ask this question. And here's how it goes. So think of a convex body, any convex body, say A inside R4. And let's look at the 6 coordinate projections from R4 to R2. There's 1, 2 projection, 1, 3 projection, 1, 4, 2, 3, 2, 4, and 3, 4 projection. And for each one of them, we look at the image of A. It defines a convex figure inside the plane, so we can measure the area of it. So in this way, we'll get 6 numbers, each one of them being the area of a convex planar figure. And the question is, which collection of 6 numbers arise this way? So for example, if you start with the unit ball in R4, the 6 shadows of it will all be unit circles. And each one of them has the area pi. So pi, 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 pi can certainly arise this way. You can try some interesting polytopes. For example, the convex roll of 4 standard basis vectors together with E1 plus E2 and E3 plus E4. So basically, all the projections will be the standard triangle, except for the 1, 2 projection and the 3, 4 projection, where you also have a point at 1, 1. So in this way, you will get the areas 2, 1, 1, 1, 1, 2, if you prefer the algebraic geometer's convention that the triangle has the area 1. Otherwise, you multiply by 1/2. And clearly, the question we ask is independent of scaling, so you can ignore that 1/2. Here's the algebraic geometry counterpart. I really like this question because when I pose this question to many algebraic geometers, they find it ridiculous that the answer to such a simple question is unknown. And I also believe that the answer will remain unknown for quite some time, but who knows? But the question goes as follows. It's a very concrete question again. So think of an irreducible surface S in P1 to the 4. And as before, we look at 6 coordinate projections, 1, 2, etc., until 3, 4 projection. And for each one of those projections, we look at the degree of the covering map from S to P1 to the 2. In this way, we get 6 numbers. And the question is the same. Which 6 numbers arise this way from an irreducible surface S? You can quickly see that the data of these 6 numbers is the same as the data determining the homology class of S. So the question can be equivalently formulated as characterize the homology classes of irreducible surfaces in P1 to the 4. So for the first question on convex bodies, I'm going to later show you the full answer. For the second question, I'm going to show you some partial results together with a very optimistic conjecture that might characterize such homology classes. But one thing to notice here is that without the convexity assumption or the irreducibility assumption on the surface, the answers to the corresponding questions are trivial. Because, for example, in the convex geometry setting, you can just place 6 pieces of planar figures in appropriate angle in some completely unrelated way. And you can realize any 6 tuple of non-negative numbers as the projection areas. If you want them to be connected, it's fine. You can connect them by very thin strings and your thing will be connected. And any 6 tuple will be realized. And similarly for the question 2, if you drop the reducibility assumption, this is just a question about the effective form of cycles inside P1 to the 4, which has the trivial description. So the answer, I'm going to formulate it in terms of triangular hyperfield, although this is not really essential for today's talk, but it will be essential for tomorrow's talk. So as an appetizer, let me formulate the results in this way. For the very precise version of what this triangular hyperfield is, I'm going to refer to tomorrow's talk. And today I'm going to roughly tell you what it is, together with precise definitions of the objects that we will actually going to need in the formulation of the statements. So this triangular hyperfield is the quotient of the complex numbers under the absolute value map. So there is a complex numbers, and if you take absolute values, the image will be the non-negative real numbers, which you view as a multiplicative monoid. And this is a homomorphism of multiplicative monoids. And I'm going to consider the extra structure, the so-called additive structure on the target, which is just the ternary relations expressed as A plus B plus C is equal to 0. And I'm going to say that A plus B plus C equals 0 in the target exactly when there is a triangle with side lengths A and B and C. So if you think about what a field is, it's completely determined by 2 pieces of data, how you multiply and this ternary relation, A plus B plus C is equal to 0. And this absolute value map is a homomorphism in the sense that it both preserves the multiplicative structure and the ternary relation, which says A plus B plus C is equal to 0. So tomorrow, I'm going to tell you what precisely this T1 is as a hyperfield or a pasture or a tract. There is an obvious deformation or an isomorphism of T1 to the same structure that we call TP for every positive number P. It has the same underlying set, which is the set of non-negative real numbers. And you say that A plus B plus C is equal to 0 exactly when there is a triangle with side lengths 1 over P power of A and B and C. And this is just, I use this isomorphism that goes A to the P to define a structure on T to the P. And the reason why you would be interested in doing this is that they have an interesting limit. So it's a very interesting exercise in calculus to show that in a precise sense, the limit of T to the P as P approaches 0 is a very well-known and beloved object called T0, known as the tropical hyperfield. So it is the same multiplicative monoid, non-negative real numbers, where you say that A plus B plus C is equal to 0, if and only if the maximum among the 3 numbers is achieved at least twice. Okay, so you don't really need to know for today what T1 or TP or T0 is. You only need to know this definition of Grassmannian 2,4 over TP. And this is a very concrete definition in terms of inequalities, a particular subset of R to the 6. GR24 over 2TP is a set of non-zero 6 tuples, Pij, such that there is a triangle with side lengths P12 times P34 1 over P to the power, P13 times P to the 4 1 over P to the power, P14 times P to the 3 1 over P to the power, modulo the scaling by the positive real numbers. Here, by a triangle, I include the case of not degenerate triangles so that this defines a closed subset of R to the 6. And you might recognize this as the defining equation, so-called the Plücker relation of GR24 interpreted over TP in terms of the ternary additive relation introduced before. But it is what it is. It's a concrete subset of R to the 6 modulo scaling. A non-trivial result, a rather challenging exercise, again in multivariable calculus, is to check that GR24 of a TP for positive P is homomorphic to a 5-dimensional compact ball. And this is a challenging exercise because this GR24 TP, the defining relations, do not give you a convex set. So this B5 is a non-convex compact ball. So its boundary will be a 4-dimensional sphere. And as P approaches 0, this compact ball approaches the beloved object in tropical geometry, the so-called tropical Grassmannian Gr24 T0. You might know that that is a piecewise linear 4-dimensional object. Again, a very interesting non-convex structure. And here's the theorem. And that answers the first question I posed about the convex bodies. The answer is that there is a convex body, A inside R4, with given 6 projection areas, exactly when the corresponding point Pij defines a point in GR24 T2. So it is very easy to tell you, if give me a 6 tuple of non-negative numbers, to tell you whether there is or there is not a convex body A with 6 given projection areas. You simply compute the Plücker relations and see if the relations are satisfied over T2. I'll show you later where one direction, the necessity of the Grassmannian 2-4 condition, follows from the Hodge-Index theorem in algebraic geometry. And the converse question, the construction of the convex body given the 6 Pij, is in a sense more interesting, especially on the boundary. So at one point, I and my collaborators achieved a solution in the interior of this 5-dimensional ball by what we think is a very nice, clever computation. But then we were stuck on the construction on the boundary. And we have tried all sorts of ways. In particular, we have tried all the ChatGPT kind of things because we thought that this was a completely fair question for them. Right? Especially if I give one particular point on the boundary, for example, 3, 2, 1, 1, 2, 3. This is a boundary point because there is a degenerate triangle 1, 2, 3. So I asked in all versions, all the $200 versions of the available ones, can you find me just one A with projection areas 3, 2, 1, 1, 2, 3? And after like 200 tries, we never got anything close to the final answer that got it. So this could be an interesting test case. Okay, so just to give you a feeling why the boundary case might be interesting, let me give you a toy example. This is a trivial problem. So we ask the same question from R3 to R2. So there are 3 coordinate projections. This is codimensional projection. So we have 3 projection areas. So given P1, P2, P3, how do we find A? In this case, as you may imagine, there are no restrictions on P1, P2, P3, other than that they should be non-negative. But any sane person, when given this problem, will say, oh, it has obvious solution. There's a canonical solution, and you're going to draw this picture. Hey, try the cube. What should be the length of the cube? One length should be P1 inverse. The other length should be P2 inverse. The other length should be P3 inverse. So that if you compute the projection areas, it will be the inverse of Pi, Pj. And if you want to make it into P1, P2, P3, you just multiply by the appropriate constant, which turns out to be square root of P1, P2, P3. So that completely solves the problem on the interior of the solution space. And you notice the nature of the solution is such that if you approach the boundary, as you drag your P1, P2, P3 to the boundary case, maybe one of them approaches 0, your solution diverges, and you have no idea what the solution is on the boundary case. Of course, in this case, it's not hard to separately deal with the boundary case, but the obvious solution diverges. And exactly the same thing happens for the other case. So this is the conjectural trichotomy that I believe. So everything underlined in red is conjectural. So I really don't know. So you can pose this kind of questions for full-dimension K projections for any K. And as you can believe, full-dimension 1 problem, the problem is trivial or very easy. Full-dimension 2 projection problems, I think it is understandable. I don't know the answer for sure, but I'm going to show you a conjecture to the problem in this case, which I believe someone can solve it in the near future. I also believe that if somebody asks the question, which enters 3 tuples of numbers can be realized by full-dimension 3 projections of the convex body, my belief is that this is an impossibility. Again, I don't know, but my intuition is coming from the similar trichotomy known in combinatorics, in particular matroid theory and related incidence geometry. So rank 1 matroids are trivial. Rank 2 matroids are not trivial, but easy enough. Rank 3 matroids, especially if you ask about realization questions, they tend to be impossible. I'm going to show you in lecture 3 that why I believe that it is even very hard to formulate a reasonable conjecture for full-dimension 3 projections. And I'm going to show you some tools which can be probably used to show that if anybody comes up with a reasonably simple formulation of the conjecture for the full-dimension 3 case, you can use these tools to probably disprove them. So I'm going to need some definitions, general definitions in algebraic geometry to continue the discussion. The definition is for any smooth projective variety over C, where variety means reduced and irreducible. And again, this is important for us. There are 3 layers of realizability, where in the first layer, you say that an internal homology class is realizable over Z, or with coefficient Z, if there is a subvariety 3 inside X with a given homology class. That's the first layer. And the second layer is about the rational coefficients. We say that the homology class is realizable over Q if some rational multiple of the homology class is realizable over Z for some lambda non-negative rational number. And lastly, you say the real homology class is realizable over R if it is a limit of classes realizable over Q. So there are 3 definitions here. Okay, so let's ask this question of characterizing realizable classes when X is a very simple variety like P1 to the 4th. Here, I'm going to identify the 6 tuple of numbers P1 to up to P3, 4 with the corresponding homology class written in the obvious way using the Kenneth decomposition. I have a typo there. I think P34 in front of point plus P1 plus P1. In any case, the theorem goes as follows, and it's very similar to the answer to the convex geometry question. If you have a rational homology class of P1 to the 4, say Pij, it is realizable over Q if and only if Pij belongs to GR24T2. And this makes sense because GR24T2 is defined up to scaling, and same for realizability over Q. And as a side remark, it is interesting to compare this to the characterization of complete intersection classes over Q inside Q1 to the 4. Those surfaces that can be defined by two equations. I haven't defined precisely what complete intersection class over Q is, but you can imagine what it is. It is a complete intersection class over Q if some multiple of it is literally a complete intersection of two other surfaces. And that holds exactly when Pij belongs to GR24 T1. And GR24 T1 is a strict subset of GR24 T2, although they won't fit each other. It's a ball included inside a ball. Okay, so here are some examples. So consider the case of 1, 1, 1, 1, 1, 1, which corresponds to the triangle 1, 1, 1. So this point belongs to TP for everything. And this class is realizable over Z, but it is not a complete intersection class. I'll leave it as an exercise to justify the assertion that this is a realizable class. It's an interesting surface, very nice surface, not related to the diagonal. Oh, this way. But what is interesting here is that 2, 2, 2, 2, 2, 2 is a complete intersection class over Z. So here you see that when asking about the realizability question, they asking it up to a multiple and sometimes simplify the answer. Another more interesting case is the case of 1, 1, 1, 1, 1, 3, which corresponds to a triangle with 1, 1 squared 3 as side effects. And the claim here is that this class is not realizable over Z, but 2, 2, 2, 2, 2, 6, which is a twice of it, is the class of a irreducible surface, so realizable over Z. So I'm not going to justify it now, but I'm going to tell you later a more stronger general statement from which this assertion follows. Yep. So here is one condition on the realizability over Z. So if something is realizable over Z with Q1 to positive, then it must satisfy the inequality P34 at most Q1 3 P24 plus Q1 4 P23. So one of the dehomogenizations of the Plücker only Q1. And the proof is very simple. You look at two coordinate projections, pi 3 and pi 4, and just observe that S is contained in the intersection of projection and inverse images of pi 3 and pi 4. And the very optimistic conjecture is that in addition to GR24T2 condition, which is necessary, this inhomogeneous condition will essentially characterize the realizability over Z, when in the case is X is P1 to the 4. Okay. So this is the statement that explains the 1, 1, 1, 1, 1, 3 example. So what you can prove is that if you have a point Pij in GR24T2, not up to a multiple, because we are trying to answer questions about the realizability over Z, what you can show is that in case when Pij are co-prime, then given any prime L, either Pij is realizable over Z, or L times Pij is realizable over Z. So by the previous theorem, we know that 1, 1, 1, 1, 1, 3 is not realizable over Z. And by this theorem, we know that 2, 2, 2, 2, 2, 6 is realizable over Z, or really any other prime power of 1, 1, 1, 1. One thing that is interesting about the proof of this statement is that the proof is transcendental. So we choose a suitable K3 surface and the map from S to P1 to the 4. And I think it's an interesting question or project to try to show this without transcendental method, without very hard complex analysis, because this is a very concrete question that anybody can try and have fun. So a concrete question would be that the same statement holds in characteristic B. Okay. So now I'm going to formulate the n-dimensional versions of the same statements, the realizability questions. And the main definition here is that of Lorentzian matrices. You say that n by n symmetric matrix Pij is Lorentzian if all entries are non-negative, and Pij has at most one positive eigenvalue. Okay, so one lemma that plays an important role in the talk that I'm going to give tomorrow, the joint work with Matt Baker, Mario Kumar, and Oliver Lorentzian, is this very simple lemma that probably goes back many, many years. But we are very proud to find this simple lemma in our simple set. So probably Paley knew this, or perhaps the Heron of Alexandria might have known this, because this is exactly the statement that we need to know. By the way, the Heron of Alexandria is someone who may have lived about 2,000 years ago in Greece somewhere, who figured out the formula for the area of the triangle in terms of the three side lengths A and B and C. And his answer is that it's a square root of some polynomial in A and B and C, and maybe divided by some something. And for that formula to make sense, you need to know that you can only take the square root of a non-negative number. So presumably, he must have known that the thing that he's taking square root of is non-negative, and it's contained in this lemma. Okay, so the statement is that the P12, P13, P14, P4, P34 satisfy the three triangle inequalities over T2 if and only if this symmetric matrix, 4 by 4 matrix, with 0 on the diagonal is Lorentzian. In other words, it has exactly one positive eigenvalue, or at most one. And the proof is very simple, and I'm going to show you shortly. And it is based on the observation that you can test the Lorentzianness of a matrix by testing the signs of principal minors. So if something is Lorentzian, 1 by 1 principal minor should be non-negative, 2 by 2 should be non-positive, 3 by 3 should be non-negative, 4 by 4 should be non-positive, and so on. And this is exactly the characterization of Lorentzian matrices. And when you have 0 on the diagonal, the good thing is that you don't have to worry about 3 by 3 principal minor. It's just about testing 4 by 4 or the determinant, deciding the non-negativity of the determinant of this 4 by 4 matrix. And you can just compute the determinant, and you will get some degree 4 polynomial in Pij. And the assertion is that that's non-negative exactly when there are 3 triangle inequalities in that particular form given by the Plücker relations. And what's very neat here is that if you compute the determinant of this general 4 by 4 symmetric matrix with 0 on the diagonal, you'll see that you got an irreducible polynomial. But that does not mean that you cannot factor it. it has actually a very, very beautiful factorization. And that is the proof. And here is the factorization. So this irreducible polynomial determinant of Pij can be factored into 4 things. And each one of the factors tells you that the corresponding triangular inequality must be true. So this factorization has the particular form so that the sum of any 2 factors have a fixed sign. So this whole thing has a fixed sign exactly when every single one of the factors have the required sign. And that's the proof of the equivalence. So our previous result, the characterization on the realizability by convex bodies, can be phrased in terms of the Lorentzian matrices of this kind. And that admits a generalization to any dimensions. Suppose you have a product of n projective spaces of various dimensions. And let's say HI is the pullback of the hyperplane. And for every homology class, or element of the child group of X, 2-dimensional, you turn it into a symmetric matrix by pairing with IHI and HJ. So in this way, you turn homology class into a symmetric matrix Pij. And theorem in this setup is that the A cut is realizable over Q if this matrix Pij is a Lorentzian matrix. And I later realized that you can omit the algebraically closeness assumption if you declare realizability by reduced and irreducible subschemes over K. And let me briefly indicate how the proof of this theorem is. As you can imagine, one direction, the necessity simply comes from the Hodge-Index theorem applied to the resolution of singularities of the representing the irreducible surface. The construction is based on a construction of a very particular kind of surface that we call prolific. We say that the smooth projective surface S is prolific if it does not contain any negative curve, and every net divisor is numerically equivalent to a semi-ample divisor. So the first condition on the no negative curves tells you that the net cone of your surface is as large as possible and is completely round. And there will be many, many points on the boundary, rational points on the boundary of this net cone. And you require that every such rational point on the boundary of the net cone is actually semi-empty. It defines a map to something. And these maps you use to construct or put your surface inside the product of projective space to hit basically any realizable homology class. So what we actually show is much stronger. So what we show is that basically up to a multiple, any realizable homology class can be realized by this single surface given N. And the main construction is the construction of this prolific surface of given Picard rank N. And our proof works over characteristic 0 or when K is uncountable. So if you like to think about things like surfaces over FP bar, I think it will be interesting to try to construct one of these guys over something like FP bar. We don't know how to do this. Okay, so that's the main results about the product of projective spaces. And before moving on to one more algebraic geometry thing, let me just tell you the concrete conjecture about 4-dimension 2 projections of convex bodies in Rn. So the question here is, if you have a convex body A in Rn, you can look at all the n choose 2 4-dimension 2 projections and ask when is this symmetric matrix realizable as projection volumes of a convex column? And the conjecture, obviously, suggested by the results in algebraic geometry, is that such Pij is realizable if and only if the corresponding matrix is Lorentzian. We do not know how to show this, but except when n equals 4. So let me tell you very briefly about the possible shape of this kind of questions when you ask it not for some simple things like Q1 to the 4, but any smooth projective variety. So you say that Rkx is a set of all k-dimensional classes realizable over R, say inside the finite dimensional vector space of cycles on X modulo homological or numerical equivalence relations. It's a some subset, and almost always it's not a convex set. So we're not asking about some question about some convex cone of cycles. This is a non-convex set. For example, when X is Q1 to the 4, we have seen that this set is Q1 to 42. And again, in case of codimensional 1 cycles, the answer is reasonably simple, yet not entirely. So for example, consider a case when X is a surface. And the question here is which classes are the classes of irreducible curves? And we kind of know the answer. So this is R1X is the union of the net cone and a set of isolated rays. So these isolated rays, which are like negative curves, which may have accumulation point, but that accumulation point will be at the boundary of the path. So there will be a huge chunk of realizable classes, which consist of positive cycles, and there are some sporadic negative cycles, and they can be very erratic. So it makes sense to ask about the positive realizable cycles. And in general, when X is an n-dimensional thing, the codimension 1 realizable classes, if you take the interior of it, so that you kill all the sporadic negative cycles, you can show that it is actually the cone of movable divisors. The divisors, the cone generated by the divisors that are movable. The base locus has no fixed component. In general, the only thing we know how to show is this one. I mean, it has a surprisingly, it was kind of non-trivial to show this. What is generally true is that the interior of Rkx, the realizable locus, is non-empty. So there are many, many irreducible classes inside any X. And perhaps an interesting example is that the interior of this realizable locus, even for one-dimensional cycles, can be disconnected. So the example, I think the easiest example you can see this is where you take the quintic threefold Q inside P4, and you take one of its 2,875 lines, and you arrange it so that this line has normal bundle O minus 1 plus O minus 1. And if you blow up this line bundle, you get the exceptional divisor E inside the blow of X. And then you see that the cone of effective curves has this picture. So on one side, the yellow part is the interior of the classes of irreducible curves. On one side, you see the irreducible curves, actually movable curves that are contained in the exceptional divisor. So they move around the exceptional divisor, but they can never escape it unless it decomposes into 2 or more irreducible components. And then you move around, and then it can go into the other realm where it can there the 2 components or more can merge together and form another part of the realizable locus. So it makes sense. So I think you can imagine that given X, there will be many sporadic negatively sitting inside subvarieties, and the realizable classes inside those subvarieties may have non-trivial contribution to the realizable class on the whole. So again, it makes sense to ask about the positive realizable classes. And this is our very optimistic conjecture that these classes shows a very structured behavior in the case when the cycle has dimension 2. The conjecture is that the two conditions are equivalent for universally pseudo-effective two-dimensional class, whereas universally pseudo-effective means that arbitrary pullback is pseudo-effective. So this is the replacement for the netness of the cycles of higher codimension, where once it was realized that the netness for higher codimension cycles is not as nice as a case of a codimension 1 cycle. If you don't like universally pseudo-effectiveness condition, I think it's already very interesting and very strong assertion to just restrict our attention to the case when X is a homogeneous variety, where you can replace universally pseudo-effective simply by pseudo-effective. And then this becomes a very, very concrete assertion. The conjecture is that the homology class is realizable over R exactly when, in the bilinear form, it induces on the real part of H11 has at most one positive eigenvalue. So this is exactly the statement that you have seen for Q1 to the 4, or more generally, product of n projective spaces. I like this question because it seems to me that there are very, very few things we can try to disprove this conjecture. There is always things you can try to prove this conjecture for a given X, but it's very hard to think of anything that might disprove this statement. So in the process of either trying to prove this or disprove this, we might be able to create some interesting math. The very weak evidence, other than the case of Q1 to the 4, is the case of Grassmannians, where there are basically no condition, because H11 here has dimension 1. So one positive eigenvalue condition is vectors. And also, like this is homogeneous, so universally pseudo-effective condition is also vectors. It's just the effectivity. And the condition is that for any two positive numbers, A1 and A2, the corresponding linear combination is realizable over C. When one of the two numbers is 0, there are some cases where you have to distinguish depending on the values of E and N, but you can also completely understand these boundary cases. Yeah, it's amusing to compare this with another conjecture of Dolbachev and Ryder, so no, maybe 80s or 90s, which says that the corresponding linear combination of Schubert cycles, A1 and A2, is realizable by a smooth surface in GR24, then A1 must be at most 3 times A2. So if this conjecture is true, and combined with theorem 8, you have the following picture for the realizable cycles in GR24. So there is some interior cone, which corresponds to the smooth surfaces. And as you go outside, but still inside the effective cone of cycles, you can still represent them by irreducible surfaces, but necessarily singular ones. So tomorrow, I'm going to continue this story in a slightly more general setup and introduce properly various facts and precise definitions of triangular hyperfields and various tricky statements you can make out of it. And for now, I'll stop.